Test. Good evening, everyone. I'm Dave Halleck, the Superintendent of the National Parks of Eastern North Carolina. It's my pleasure to welcome you here tonight on this beautiful night at Wright Brothers National Memorial. I want to start by thanking our staff for partnering with NASA tonight to bring Dr. Balaram to the park, as well as AeroVironTech for bringing the working model of Ingenuity here to the park. Wright Brothers Memorial is a place where we can be inspired by the amazing accomplishments of Orville and Wilbur Wright. If you were not aware, our staff continue the legacy of the Wright brothers through their use of technology in everything we do here. For example, if you take a moment and turn around and look at the big Kill Devil Hill behind you, you might know that just a year ago we started mowing that hill with a remote-controlled mower. In addition, about a year ago, maybe a little more, Wright Brothers National Memorial brought the first autonomous shuttle to any of our 423 national parks here at Wright Brothers. And what was amazing, I still remember this, the day before we launched the autonomous self-driving shuttle that went from here all the way around the big Kill Devil Hill and transported thousands of visitors, I remember watching the news on April 19th, 2021. And it was on that date that I heard one of Dr. Balaram's colleagues, Mimi Ong, make the following statement. She said, "We have been thinking for so long about having our Wright brothers moment on Mars, and here it is." That was the day that the Ingenuity helicopter flew on Mars, right before our autonomous shuttle. It was really fantastic. So tonight, it is my pleasure to introduce Dr. Bob Balaram, the originator of the concept that became the Ingenuity helicopter on Mars. Dr. Balaram is the principal member of staff of the Jet Propulsion Laboratory in California at the California Institute of Technology. He received his PhD in Computer and Systems Engineering from Rensselaer Polytechnic Institute in 1985, where his doctoral work addressed the control of highly nonlinear systems. He has been at the Jet Propulsion Laboratory ever since and works in the area of early descent and landing, modeling and simulation, telerobotics, technology, and mobility concept development. Wow. He served as the chief engineer during the Ingenuity helicopter's development, test, and operations, and Bob has also served as the initiative lead for a strategic research and technology development effort to develop science helicopters on Mars as a follow-up to the success of Ingenuity. It is my pleasure to welcome Dr. Balaram.
Okay, thank you so much. Yeah, it's been a fun day. I've been giving a bunch of talks earlier in the day, which were more focused on comparing the Wright brothers' experience with our experience. I visited this park a few months ago in the midst of winter, and I was really struck by all the similarities that I saw. The wonderful museum out here, and then one of your volunteer folks, Karen, got me thinking about the idea of maybe I should come back and do a more dedicated program out here where we would honor the Wright brothers and expose people to the work we've done on Ingenuity. So here I am, talk number 3. This one is a bit different from the ones that I did earlier in the day, which were more about directly comparing the two experiences. This is a longer talk, focusing more upon the actual Ingenuity and its development, the story behind how it got to be. And you'll see a little bit of overlap, but not too much. So up there is one of my favorite pictures. It's taken by Ingenuity from a height above the surface of Mars. That region of Mars is called South Zeta. Zeta is the Navajo word for sand dunes, land of sand dunes, I believe. And when the scientists were designing the mission of the Perseverance rover, which is what the rover that took Ingenuity to Mars, they had divided up the area into different sectors, and each sector got a name based upon, different geological features. So it turns out that we landed in Zeta on Mars, in Jezero crater. And the way you always recognize an Ingenuity color image is, you see the thing on the left? That looks like a little ball. That's one of Ingenuity's feet. Every one of Ingenuity's color photographs will have a little foot sticking in the photograph. So it's kind of like, a selfie in every photograph, if you will. As was mentioned, I was the chief engineer till fairly recently, and I've since handed over the reins to younger members of the team, and somehow in the process acquired the emeritus label, which I'm not fully sure I'm comfortable with, but so be it. But it's not my absolute full-time favorite. That we'll get to in a minute. That's my absolute favorite image. It's a black and white image, and it's of the shadow of Ingenuity. We flew around noon, so around the sun on that first flight, and the sun was directly overhead. And what you see is the shadow of the counter-rotating propellers, frozen in time by the frame of the shutter frame, and the solar panel and the fuselage and the legs. And it's a great photograph from that first flight, and that actually is, even though it's black and white, it's my absolute favorite. So I'd like you all to sort of visualize a place on Mars in Zeta, and on the left you have an image from a really good, wonderful camera on an orbiter that is circling Mars. It's called the Mars Reconnaissance Orbiter. And there is a camera called the high-rise camera that's on that orbiter, and that's the kind of image that you can get from orbit. On the right is that same area just blown up so that you can see what that place looks like. And if you're a scientist and you're looking to see where to go, you get an image like that and you have to make a decision. Am I going to send the rover all the way around? You see that white path? That's the path that the rover eventually took to get to that place. But when we first landed in the top right corner there, we didn't know whether this place was worth going to. I think the scientists, they thought it was a good place to go, looking for sediments from the bottom of this ancient lake bed, which could hold evidence of early life on Mars. Once upon a time, this Jezero crater, which is where this is, had water. It had rivers running into it, bringing in sediments from the upland. And so if there had been life at that time, Earth was developing life at just about the same time. And then, of course, Mars lost its water. So if there is primitive life, its evidence of it could be in the sediments of this lake. And the Perseverance rover's job is to collect samples, the right samples, so that eventually they can be returned to Earth and studied to make a determination if there was life elsewhere at that time. So you're landed on the top right, and you're trying to decide to get whether it's worth going to the bottom there. You notice it's a pretty circuitous route because right in the middle is Zeta, the sand dunes. So the rover can't really drive across that region. And if you look at that image, that's what it looks like from orbit. And that's an image of the exact same area taken by Ingenuity. So you can see that there's a tremendous improvement in the quality of the image. And this is what allowed scientists to sort of make the call and say, you know what, it's going to be worthwhile to go there and investigate a particular kind of rock. So we started off as a technology demonstration of can you fly in the very thin atmosphere of Mars. Mars, the surface density of the air compared to what we have here is 1%. And so whether flight is even possible, physics says it should be possible, but can you actually build a system that allows you to fly there? So we were only supposed to go and just prove that. We were given a chance over a course of about 30 Martian days, which is almost the same as an Earth day, slightly longer, to see whether we could fly. But it turned out that we started getting images like this. And the scientists said, wait a minute, this is a great scouting value for us. And the rover drivers started getting images like this and said, you know what, we can use this to plan paths. Okay, we can decide whether to, squeeze our way through a few sand dunes here, or do we have to take a detour. So this kind of aerial imagery, which, here on Earth, we have drones every day doing this kind of imagery and showing the value of this kind of aerial opportunities to really get detail. That's what we're able to do on Mars, an unprecedented resolution. And it's all based upon a cell phone style of camera. This is not even a fancy camera that's taking the image. It's a little 2-gram, a tenth of an ounce camera like you have on your cell phone. Not this cell phone, like if you went back to 2013 and you looked at your phone, it's the same, something in the Samsung Galaxy or the other. It's the same processor, same cell phone camera. So that's what you get with having something like an aerial asset on Mars. And if you take enough of those images using computer technology, you can actually reconstruct 3-dimensional views of the surface. So this is well understood technology where if you take what's known as wide baseline stereo images from multiple locations of the same place, you can build up 3-dimensional maps like this. And again, the scientists just love this kind of stuff. So in order to really get this, you need those aerial views. You need something that can, I don't have a pointer, but if you look closely on the right, you see a green line. That is the actual path that Ingenuity took to take those images. And those 2 yellow markings were the 2 high-resolution images that were taken to achieve that 3-dimensional view that I saw. So you need something that can go there, hover, take a picture, move over by 50 or 100 feet, take another image. And that kind of capability is what a helicopter provides on Mars, that even a fixed-wing aircraft could fly by very quickly, but to be able to actually persist and look at something, to examine something closely, to land precisely at a spot, that's the kind of mobility that a helicopter brings. And that's what enabled us to get those images in a little place called Peifu, which is again a scientist name based on some French geographical feature. They try to assign names so that it's convenient for them to refer to them afterwards. So you find names like Seta and Peifu and various other unpronounceable places depending upon which tags they used. So now in order to do this, you really need a really great team. Mimi Ong was mentioned. She was a tremendous leader in the sense that there was no obstacle that was too big for Mimi. I likened her to the sharp point of a spear, and once she decided to go in a direction, you knew you could follow, and whether there was a financial issue or a staffing issue or somebody playing politics, you knew that Mimi would get to the end of it and get us there. She has since left JPL, by the way, but she's moved on to other things last year. But there she is in the middle with standing next to me, and we also had other people. We had folks from AeroVironment who were here earlier in the day, demonstrating a terrestrial version of Ingenuity, which they basically cobbled together with leftover parts from Ingenuity. Now, that one is a little joystick model. What we have is a much more autonomous system that's actually flying, hundreds of millions of miles away. We had folks from the NASA Ames Research Center in Northern California, folks from Qualcomm. They're the ones who make your, smart processor phone chips. So we work very closely with them. NASA Langley, up close by here in Virginia. So NASA Langley Center. And Solaro, a company that built the solar panel for us. And Lockheed Martin in Denver that basically built the gadget that gently lowered us onto the surface right at the end. So it's a large team that was required to put something like this together. And it's really, we were chasing a dream, if you will. I must point out that when this idea first came, there were a lot of skeptics. Even the chief engineer at JPL didn't think it was possible, and they thought it was a stupid, foolish thing to do. The air is too thin. You can't really build a spacecraft, let alone an aircraft, to get there and do things. So we had a lot of skeptics, but we persisted. And in some ways, and this is what I kind of focus a little bit more on the talks that I give in the day, is very much like another dream. There are a lot of people who said that couldn't be done, and the Wright brothers' singular achievement in achieving controlled flight, that was really what set them apart from everybody else. And so we were very inspired by them. And in fact, the quote here is, if you all worked on the assumption that what is accepted as true is really true, there'd be little hope of advance. And I think that captures, if you will, what kind of kept us motivated. So let's talk about some of the challenges specific to flying on Mars. That's a view of Earth from 100,000 feet. At 100,000 feet, the density of the air on Earth, matches the density at the surface of Mars. If I have a cubic meter of air or a cubic yard of air, on Earth it's about 2 pounds right here. If I stretch my arms out wide and think of a cube, it's about 2 pounds of air. The same amount of carbon dioxide air on Mars, on the surface of Mars, would be less than an ounce. So if you remember anything from your high school physics, or in order to get something to fly, you got to generate lift. And the way any aircraft generates lift is by pushing stuff downwards. But you push enough stuff downwards fast enough, you get enough thrust going upwards. But the air is so thin that you got to push a lot of air downwards, right? That's what it comes down to. But physics says it's possible. The question is whether engineering-wise we can achieve it. Now, so that's one big challenge. The other challenge is we're trying to build an aircraft, but it requires space travel, okay? It's not normally something you associate with aircraft. So getting there is not easy for an aircraft. You got to hitch a ride. That's an Atlas rocket taking Perseverance with Ingenuity on the top. Right at the top of that fairing cone out there is the Perseverance rover upside down, and on its belly is little Ingenuity. So we're actually the highest point on that rocket. And this is a very violent event. A rocket is basically a controlled explosion. You get acoustic vibration loads of 60, 70, 80 Gs, 80 times the force of gravity in vibration loads as you go up. So this little aircraft, which you're trying to build to be very lightweight so that you can fly, has to survive all of that, like any other spacecraft. We're also, being a passenger or a hitchhiker on what is a major flagship mission for NASA. This is, after all, a mission that is going to go there and look for signs of past life. I mean, how cool is that? If we find, whether the answer is yes or no, either way, it's a very dramatic answer that we'll know in a few years. And we're this added-on gadget, drone, if you will, if you want to be slightly pejorative about it, but you can call it drone, I don't mind. Helicopter, rotorcraft. We're adding this little technology demonstration that represents some risk. What if it falls apart, as this thing is taking off, or it causes some problem, or it interferes on the radio, with this wonderful multi-billion-dollar mission. So we have to be a very, very good passenger, and that in and of itself has a lot of challenges. For example, one of the things that we have to do is to be very, very clean. We cannot carry any biological spores, very few. We cannot do something called outgassing. In the vacuum of space, even the slightest bit of volatile stuff tends to go and deposit itself onto sensitive surfaces like instrument lenses and things like that. So it's a very major challenge to be accompanying a flagship mission. It's also very far away. Now, it's cloudy here and it's not quite midnight, but a little bit after midnight, Mars will rise on the eastern horizon, and it's so far away that even radio waves traveling at the speed of light take many minutes, 10 minutes sometimes, to go from here to Mars, and then 10 minutes to get a signal back. So there's just no way in which you can joystick this thing, okay? You can't hire your most talented teenage kid to joystick this drone. It's got to be highly autonomous to be able to operate by itself. So what we do with Ingenuity is we actually send it a bunch of commands. We say, go here, fly there, go here, take a picture, come back, or go somewhere else and land. And we send that off, and it's not even just a light delay. Our radio signals have to hop from the deep space network, which NASA has, to an orbiter on Mars to get down to the surface to the rover, which then sends the commands to Ingenuity, and then Ingenuity wakes up and flies. In fact, earlier today, we uplinked commands for a 30th flight for Ingenuity. And I was just looking at my Mars clock. It's early in the morning on Mars, I think around 3 a.m. Around 2 in the afternoon Mars time, which is roughly about 12 hours from now. If everything goes well, we would have flown our 30th flight on Mars, and we will know later in the morning. We'll get the data back, and we'll see whether we succeeded or not. So we've been flying 29 times. We'll see whether we get a 30th one under our belt by tomorrow morning. So it's quite a challenge to operate from that distance. And conditions are not pretty good. It can get down to minus 90 degrees centigrade. That's about a minus 130 degrees Fahrenheit. So it gets very cold. That presents challenges for things like batteries. Most of your regular electronics doesn't like to get that cold. We ended up using a lot of commercial off-the-shelf electronics because they had the capacity and the performance. A lot of NASA hardware tends to be of an older generation because it's more proven. We had to go with the fastest processors, like cell phone processors, a lot of commercial chips which are not designed for these kinds of temperatures. And so that's just on the temperature side. There's also radiation on the way to Mars and at Mars. So you got to make sure that these electronics you send won't get hit by a random cosmic ray from somewhere in the galaxy and get upset. And that's literally what it is. It can change a 1 to a 0 on a computer. That's what an upset does. Or if it's more damaging, it can actually burn out the part. So there are environmental challenges that typically you don't find for aircraft: the temperature, the radiation. So I like to think of this as not just an aircraft. It's a spacefaring aircraft, first of a kind, with all of those challenges. And no wonder we have those skeptics in the beginning. They said, how can you do this? Because you might be able to fly, but can you do all the rest of the stuff that it's going to take to make this mission happen? Well, we did fly, as was mentioned, on April 19th. That's the team celebrating. Mimi Ong is on the bottom left. Go on YouTube and find the video that this corresponds to, okay? You will see that lady levitate from a chair, jumping up and down in just sheer happiness at this flight. I'm on the top right there. Didn't get my COVID vaccine in time, so I was banished to be at home working on this. By the way, most of Ingenuity operations are done right from home. So only more recently have we actually been physically on the lab to do the operations. Except for this first flight, a lot of the stuff leading up to it, and even subsequently, a lot of it was done from home by people working through the equivalent of Zoom type of systems. So that's the first flight on Mars, and we did succeed. And that is Ingenuity. You've seen a demonstration perhaps earlier of a near clone of that, full-scale model. Of course, things were a little bit different. Back when you had a flight of the first flight here, a telegram was sent out on December 17, 1903. But we were obviously on the internet, on YouTube, on Facebook, and every other possible thing. And essentially, a large fraction of people who have a scientific interest were able to see this kind of thing in real time. So this is the connection of Ingenuity to this place. When we were putting Ingenuity together, we had a little bit of extra mass margin. I could afford to add on a little bit of something to Ingenuity as a sort of a token or a talisman, if you will, of the effort. And I was looking around. The thought was, maybe something to honor the first flight, the Wright brothers. We were thinking of perhaps flying. There's a US penny with a flyer on one side. We were thinking maybe we could put that. But then somebody on the team said, look, I have connections with the folks at Dayton, the Dayton Experience, which is where the Wright brothers, main museums are. And we talked to them, and they said, you know what, we have some fabric which the Wright brothers were auctioning back in the day to raise money to, do future flights. Fundraising is a given in any organization. You guys know it out here with the First Flight Foundation that it always takes effort to get money going. So they were auctioning things, and so there's a piece of that auction fabric that we managed to get our hands on, and the Smithsonian verified the provenance of all of that. And what you have here are two of my engineers, Chris Leffler and Josh Ravitch. I can never tell who's who. I think because they're all in the clean room wearing their bunny suits, and so it's difficult to tell. I'm pretty sure it's Josh on the right. They are attaching this postage-size swath of fabric onto a piece of tape, which they're then wrapping around a cable bundle that's just below the solar panel. Interesting story here is, when this idea came, it was kind of hush-hush because NASA wasn't really sure whether they want to publicize this. What if Ingenuity just sputters or dies or crashes? What will it look like if it's found out that, there's a piece of fabric? Eventually, they decided that they needed to reveal the information before the first flight and not wait after a crash or something to reveal it. So we had a lot of political, aspects that made us keep this kind of hush-hush. But there were a lot of practical things too. Remember I said that this mission is, the Perseverance mission is to find signs of past life. The last thing you want to do is send a piece of dirty fabric that has some microbes and fungal spores and things to Mars, and then somehow it contaminates the rover, and then you think you found life, and it actually turns out it was a piece of fabric that wasn't clean enough. So that thing had to be sterilized, and I actually sent our engineers off to Joanne's Fabric to get swatches of fabric so they could practice the sterilization techniques before they actually got to try it on Ingenuity. So anyway, so that was a little homage, a little token of, it's getting inspiration from this first flight that happened right here, this place, all the way to Mars. So as we speak on Mars, and in a few hours, that piece of fabric is going to take off and get another flight if all goes well. Okay, so let's delve into a little bit of the actual design of Ingenuity. It's 1.2 meters in diameter, which is about 4 feet. The airfoils in Ingenuity are special because the air density is so thin. Your normal wing profile that the teardrop sort of shaped wing profile is not what you use. You use something that's much flatter. There is a aerodynamic quantity called the Reynolds number, which characterizes how flow passes a wing, and we are in what's known as a low Reynolds number regime. So the airfoil is very special and tailored to this very thin air. As I said, we have to move a lot of air downwards in order to get the lift upwards. So if you saw terrestrial Ingenuity here, the blades are spinning at about 400 or 500 RPM. We have to spin at least 6 times faster in order to generate the lift on Mars. Now, Mars has less gravity. It's about a third of the gravity we have here on Earth. So that made the job a little bit easier, but you still have to spin these blades extremely fast on Mars. And the motors have to be highly efficient. Just like Charlie Taylor built a very efficient aluminum block engine for the first time to let the Wright brothers generate 12 horsepower to fly on Mars, we had to do a very special thing with our motors, and I have a slide coming up that talks about that. We have lithium-ion batteries, which can put out 500 watts of power. Our mass is at 1.8 kilograms, so that's about 4 pounds. One of my main jobs was to track the mass of everything down to the gram and the sub-gram level. And tremendous efforts in very lightweight, carbon composite lightweight stuff. We have exotic alloys which are able to absorb heat and still be lightweight. And since Mars is so cold, we had to find an insulation system that would keep batteries warm through the night. There's a very interesting high-tech insulation called aerogel. It looks almost like solidified smoke, and it's what's been used in a number of spacecraft. But it turned out that even aerogel was too heavy for us. By the time you look at the packaging of aerogel, it turns out aerogel is too heavy. And what we actually use for insulation is the natural atmosphere of Mars. It turns out that carbon dioxide gas, if you constrain it appropriately between some thin walls, can function as a perfectly good gas gap insulation. So that's what goes into building the system. So it's all driven by the physics. The way you get to the end of this game is you just follow the physics where it takes you. So let's talk a little bit about what Charlie Taylor did. He built the engine, which produced, and he built it in 6 weeks. And Matt Keenan, who was here, he actually wound the electrical motors for this, the rotor motors that we have. We have 2 of them, one on each of these counter-rotating shafts. And it took him 100 hours to do it under a microscope. And one of the reasons it was difficult is that in order to get the most possible copper into that windings there, which would give us the most efficiency, the packing efficiency of 91% you get with round wire. If you use square wire, you could theoretically get to close to 100% packing efficiency. So he wound the thing with square cross-sectional wires, which means that as he was winding, he had to be really careful about the twist of each winding that he did so that it maintained the squareness as each of those layers were built up on top of each other. And as I mentioned, there's electronics that controls the motors, which are out there in the cold. We're using a lot of exotic materials to absorb the waste heat. So every one of those things, by the way, I was mentioning earlier, has, you notice I put a little blue on that ultra high efficiency motor. That's because in reality there is a story on every one of those things, and I've just picked a few of things to talk about in terms of, and whenever you see a blue thing, it means I'm going to dive in a little bit deeper and tell you a little bit more of a story. But it's there's stories all over the place in building the system. As I said, it has to be highly autonomous. So it turns out that flying helicopters on Earth benefits from the fact that we have a thick atmosphere. Helicopter blades like to flap up and down, and in the process, it generates unwanted disturbances onto the helicopter, which make helicopter control a bit difficult. Helicopter is naturally an unstable system. But on Earth, the thickness of the air damps out this flapping motion of the rotors. On Mars, you don't get that damping. And we found out the hard way that it can drive the system into complete instability. So we had to understand new techniques in helicopter control to even let us fly in a stable fashion. But I'll get into that in a second. We have these very highly effective fast processors, which are controlling every mechanism related to the helicopter 500 times a second. They're looking at sensor data, they're looking at a laser altimeter, they're looking at all kinds of gyroscopes, inertial measurement units, they're called accelerometers, and they're processing that at 500 times a second to keep this helicopter stable. We also have a camera at the bottom of the helicopter that is looking at the ground, and it's by seeing how much the image shifts as the helicopter is flying, we can actually estimate how fast it's moving. So we're actually using a camera as a velocity sensor, and that is being done by processing images 30 times a second. On the software side, we're using the Linux operating system. That's a open source operating system that you can download for free, and by any argument is infinitely more robust than any other commercial operating system, because literally there are thousands of people who have contributed to making Linux and the entire tools that surround Linux into a workable system. In fact, after the helicopters flew, the Linux folks went back and working with us, they found out who are all the developers all over the world who had contributed in some way to making Linux what it was and the tool sets that we used on Linux. And I think about 4,000 of them got a little badge on their Linux software thing saying, they actually contributed something. Indirectly, they didn't know it, but they contributed something because they were contributing to this open source movement, which is what Linux represents.
We also have a specific spacecraft flight software framework released by JPL on open source. You can go and download it. You can't control Ingenuity with it, but you can control your own simple helicopter with it. It's called F Prime, and that is what runs on the system. Processor, this is basically today's cell phone technology is what made it possible. Our little processor at about 5 grams is about 150 times more powerful than the processor that's running on the rover. That's because the processor of the rover had to be really, really bulletproof. So they're using 1990s, whatever Macintosh computer processor, the same processor is what's being used on Perseverance. We, being a technology demonstration, could take more chances, and we had to because we needed that kind of processing power. Now it's turned out that on Mars, this little processor, which may not be quote unquote quite as bulletproof as the more ancient ones that are normally NASA would fly, has turned out to be pretty robust. We can only identify maybe 1 or maybe even 2 incidents over the last year and a half, which we could attribute to the fact, hey, maybe some radiation hiccup, something out here. But by and large, we've not had any issue during any flight, and that allows us, the sheer amount of computing we need to do command and data handling, telecommunications. We also don't completely rely upon this Linux processor from, we also have 2 automotive processors. When you, in your car and you press your brake and your anti-lock braking system does something, you're trusting your life to a little processor built by the automotive industry. It's very bulletproof, and we actually use 2. We compare what they say, and if one of them starts to fail, we switch to the other one. So we actually have a hot swap on processors that gives us a guarantee that even if something happens to this cell phone processor, we can land safely. So we have a lot of redundant flight control processors, and that's what gives us the sort of the autonomy that we need. So let's just dig a little bit more into the flight control. Some of you would have seen this video earlier. We initially thought that all we would need to do is to, fly this thing with a joystick on Earth, and then basically replicate a similar thing on the computer. It's when we worked with a 1/3 scale model in our chamber. This is a 25-foot diameter chamber that we pumped down to Mars pressures, and we attempted to fly there. We found that we really was not controllable, and we really had major issues, which sent us back to the drawing board. I'm sure it gave our management a lot of headache, but I congratulate our leadership at JPL that to stick with us despite seeing stuff like this. So that was early experiments in flight control, but eventually we built a full-scale model of just the rotor. We put the computers and the power supplies under the floor, and in 2016, we were able to demonstrate that we had stable control flight. Actually, we were a little bit surprised that we could hear this. We had put a microphone on the floor, and there was some debate, because of the thinness of the air, whether we could even hear anything. It turns out that we could actually hear it very well. We still weren't sure whether we would hear anything on Mars, because we thought maybe the fact that we're in a big metal can, helped us to hear. But there's a microphone on one of the instruments on the Perseverance rover that actually did a recording of one of our flights, and they were able to understand a lot about how sound travels in the Martian atmosphere. And it turns out that it does. The lower frequencies get through much easier than the high frequencies, and there's some interesting science that has come out of it. It just got recently published in Nature magazine. So that was a flight of that vehicle was about a little bit under 2 pounds, and it showed that yes, as an aircraft you can fly in Mars. We proved that. But now remember, I told you the pesky part of that this thing is also has to be a spacecraft. You got to build everything else. Well, actually, hang on. Let me get to the more of the testing. Yeah, let me first talk about the testing before we actually get to building like a spacecraft. So we had to characterize the aerodynamics. We ended up mounting the helicopters on gimbals. We put the helicopter at the end of a swing arm so that we could fly it back and forth in the chamber. We instrumented it with force and torque sensors at the base to see how much lift and torques we would generate. We did a whole bunch of tethered flights, free flights. We also had to end up building a wind tunnel, and I'll get to that in detail. But the vehicle that you saw was a little bit under 2 pounds. But once you put in all the computers and everything else to make it a spacecraft, that's what brings it up to 4 pounds. That's really not possible to fly that as a free flyer here on Earth. So we had to essentially like build what we call as a gravity offload system. It's really a high-tech fishing line that we tie to the helicopter that basically pulls by just the enough force to compensate for the difference in the gravities. And trust me, we had I think 3 reviews on the knots, the backup knots used to hold the helicopter during that phase, because had those knots failed, you know, the entire program would have come crashing down, literally, right? So we had climbing experts, mechanical engineers, knot experts, all in the reviews, 3 reviews, I remember that. We had to verify that we would survive the night, that we would not expend energy more than we had to keep us warm through the night. A spacecraft is a pretty violent environment known as pyroshock. So basically, in a spacecraft, when things are released or things are, you know, like, it's not done many times with just a nice motor. It's done with an explosive charge. An explosive charge will blow a bolt, and then, you know, the legs will come down on the rover, or the back shell gets released. So you have these explosive events, many hundreds of them happening on the spacecraft, and they generate shock waves. And depending upon how close you are to that particular pyro event, you can get a lot of pyroshock, which your aircraft has to survive. Spacecrafts are vibration heavy, 60, 70 Gs of vibration for such a small payload. We had a test on a Wright table. We had to make sure that we had no electromagnetic interference of any kind. So because the last thing you want is some noisy helicopter generating a lot of noise during cruise and messing up the parent spacecraft. And of course, we had to prove that we were strong enough to withstand launch. We were strong enough to withstand, you know, the descent into the Martian atmosphere, which generates a lot of G-forces. So the test program, in some ways, was more challenging than actually designing the helicopter. And had I known that it would get this complicated, I probably would not have stepped up to the job in the beginning. But, you know, you have to do what you have to do. And one example, I believe there's a gentleman from NASA Langley here. There was no wind tunnel that operated at the speeds we needed, at the density we needed. So we went to NASA Langley. They have what's known as a terrestrial dynamics tunnel. And we said, like, okay, can we, you know, use your tunnel? But it was not available. They had some issues with trying to get it onto these low speeds. So we built one with 960 computer fans. So you see them on the right. It's called an open section wind tunnel. It doesn't need a baffling or a box around it. And we put the helicopter in front of it on a gimbal. We tend to fly and test upside down because that way most of the air goes up towards the much more headroom that we have in the ceiling in that chamber. So we're testing with our own little wind tunnel that we built with 960 computer fans. Not something that I thought we would need to do. We needed to be a very well-behaved passenger. Spacecraft like Perseverance are built to Class A standards. So all of our interfaces to them were designed to be very high quality, very clean. We're carrying lithium-ion batteries. If you ever traveled, you know that the airlines are always nervous about your lithium-ion batteries. Imagine a spacecraft which is taking on this hitchhiker with lithium-ion batteries. So very extensive test program, very extensive electrical program. And even finding a place on the rover was not easy. We ended up being nestled on the belly, and you can see a picture of Ingenuity nestled there. There's normally a debris shield that protects it during the landing on Mars, that from the rocket plumes from the main landing event. That's not there in the thing, so you can see it mounted sideways. And you think like, okay, yeah, that's a nice place to put it. But we had a bit of a journey in the wilderness before we even found that location. The project really was not that cooperative with us, the Perseverance rover project, because we were this tech demo. So they tried to put us, in some really obscure places. We still managed to find ways to deploy. So eventually, after searching for all those places and designing to all these other places, they put us in the best place where, we are right underneath. And that's the system that lowered us onto the surface. So I've talked a lot about this. The parts are, even though they're commercial parts, we've done a fair amount of screening. We have tried to use all materials and all the flight techniques that would normally go with spacecraft. So that was a learning experience for all the aircraft builders on the team, to learn how to build an aircraft, but in spacecraft style. Very cool at Mars. We are running heaters. We have active thermal control using a closed-loop thermostat, much like your household thermostat. But most of our energy just goes into staying warm. At least it was till about 100 days ago, where thanks to Martian winter, we can no longer even do that. So the actual flying doesn't take much energy compared to the fact that just staying warm pretty much uses up all of the battery. And we have got very clever with the carbon dioxide gas cap. There are multiple baffles inside the enclosure that keeps things warm. And one of the interesting things about the coating there, that sort of grayish coating on the fuselage, is it's a very high energy absorbing coating, so that essentially Ingenuity warms up a lot with the sun alone. So this is very much like a reptile, it sort of soaks in the sun in the morning, warms up, and that's what allows us to sort of minimize the amount of electrical energy we would need in order to warm up for a flight. So it's got a lot of very custom thermal designs. And so that gives you a sense of what it took to build Ingenuity as a system. So now let's actually just see some of the things that she's been doing over the last year or so. So postcards. So first we went to the place where we landed was called Wright Brothers Field. The way we got there was launch on an Atlas rocket. You folks may have seen the really nice landing that for the first time there were cameras on Perseverance that were able to image the entire landing event. And so during about the 6 months on cruise, we only had to touch the battery and sort of keep it charged up a little bit. But there's nothing much going on. Everything survived. We landed. And then the very first job was to find out where exactly did we land. There's a big landing uncertainty with the rover, right? It comes down, it can land within quite a few kilometers. So the first job was to find out where we landed. And it was very important that after we land, that we find essentially an airfield. Not as smooth and flat as this one, but something with low slopes, not too many rocks, because for that technology demonstration, we wanted to give it the best chance. So we wanted it to take off and land from an airfield. Luckily, we were able to find something very close to our landing site. And they picked that as a landing field. We searched for it. Once we finally zeroed in on a particular landing field, our team basically counted every rock out there, made sure that there weren't too many rocks. Since then, by the way, we have relaxed this constraint a lot. We right now just pick landing fields from orbital images, and we just say, go for it. And it turns out that we aim for sand dunes, because sand dunes don't have rocks. So we aim for sand dunes with not too many ripples, and it turns out those make perfect helicopter airfields. But that first flight, we were extra careful, and we really counted every rock, and you can see, how many rocks of how many centimeters height were detected. And so that's Wright Brothers Field. It actually has an ICAO designation, I think JZR, Jezero, something or the other. So we picked a flight zone. We were able They dropped the debris shield that was protecting us during from the rocket plumes. They over a course of days, they made us go vertical. We got deployed to the surface. We went through a commissioning phase where we released the blades, which were locked up for the entire cruise. We did a low-speed spin, a high-speed spin to make sure motors and everything were working. And then the first flight. So this is in some sense a very important moment because I really resonate with the statement from Otto Lilienthal, one of the early pioneers of flight, who said, to invent an airplane is nothing. Well, as you can tell, it still takes quite a bit of work. To build one is something, okay, I'll give you that. But to fly is everything. So till we had the first flight, none of this is real in my view. And that was the first flight. We took off to a height of about 10 feet. So we were out of ground effect. Basically, we replicated one of the flights we did in the test chambers, just to be able to compare apples to apples. Since then, we've done a lot more. We have flown for almost 3 minutes, but that first flight was 40 seconds. And that first image from that first flight is what I showed you earlier. So that's that first flight on Mars on April 19th. And the Perseverance rover has a nice camera with zoom lenses. And they took these kinds of pictures for us. And you can see that if you fuzz your eyes up a little bit, it almost looks like a chamber test, doesn't it? You know, rock solid against that Martian landscape, goes up in the air, comes down and lands. Little bit sped up, but basically that's the 40-second flight. More flights. We did a lot of mapping. This is the flight where the microphone was from the rover helped us, understand how sound travels. We were searching for a new airfield, and you can see the swath of that's successive images from the navigation camera, which are all stitched together, and you can see the stitch effect in the middle. So that's what Ingenuity sees when it made this 270 meters flight. That's about almost 1,000 feet long flight. And if you walk the flight line here, you'll see the first 4 flights, next to marked out next to the Wright brothers flight. So we started spreading our wings. Again, that camera, watching Ingenuity come in and out of the frame is pretty cool. We're flying a little bit higher this time. So those first 30 days was great. Like a proud mother, the Perseverance rover was taking all these images because they had nothing else to do for those 30 days. Since then, we've become a more, the priorities of the science mission, and so there's not that much imagery of us. But those first 30 days was cool. This is a reconnaissance flight where we took those high-resolution images, and then the scientists said, that place looked very interesting from orbit, but once we saw it up close in these images, it's not that interesting to the scientists. To me, it all looks like rocks. So I don't know whether it's equally interesting or equally uninteresting, depending on your perspective. But we saved them a number of days because they decided not to go there based upon what we saw. We also were used by the scientists to pick targets for what the rover should do as part of their science planning. So on flight 12, this is where the rover's sampling into the rocks to pick, stuff, sediment that could be sent back to Earth, right? So these were valuable science things to do. And also some unexpected science. We found out that Ingenuity generates its own little dust storm, or dust devils, and that allowed some of the atmospheric scientists to investigate, what kind of dust transport mechanisms you have in the Martian atmosphere. So we finished the technology demonstration. We transitioned into a operational role. We have a campaign to go up into the river delta in Jezero with Perseverance in the next few months. We've been there for over 500 days. We have been through spring and summer. We're currently surviving winter. We die every night because we don't have enough battery power in the winter conditions to survive the night. But you know what, like Lazarus, we come up every morning. We warm up our batteries, we charge our batteries. 29 flights, thousands of navigation images, almost 150 color images. We even updated the software. We survived a pretty cool dust storm, had to hunker down for a few weeks. And that's the path. So the green path is where we've been traveling, and the white path is where the rover's been going. And we're all right now at the base of that ancient river delta, getting ready to go up there and explore. So what's next for us? Well, there's a sheer amount of engineering data that's come back that lets us validate our design methodologies, our test methodologies. And recently NASA announced that they will be sending 2 more helicopters with the sample fetch helicopters to bring back samples back to the rocket that's going to send up the samples to Earth. In case Perseverance, the main method by which those samples are going to come back to the rocket, in case Perseverance fails or begins to fail, 2 backup helicopters, daughters of ingenuity if you will be there to go pick up the sample tubes one at a time. Each of them is 150 grams, pretty much the size, much smaller than this microphone, but small tubes. And one at a time they'll be ferried back to the rocket that launches us back to Earth. So we have successor helicopters identified and approved. And just also to draw upon inspiration from even longer time frame than the Wright brothers. You might recognize Da Vinci's Codex flight, where something that looks suspiciously like a coaxial helicopter, at least to me. And one of the interesting things that Da Vinci said in his Codex flight is, it will make the first flight this great bird, filling the universe with awe, filling all writings with its fame and eternal glory to the nest where it was born. So in some small measure, I think we as the Ingenuity team sort of tried to do that. So thank you all for coming, and I think we have a few minutes for questions, so please. If somebody can run the microphone to whoever asks the question.
I'll just stand up. What's the longest flight, time-wise?
We've done almost 3 minutes.
3 minutes?
Yeah.
Okay.
Yeah, and I have time. Well, the main constraint we have on flight length, as I said, is not the energy, because we actually have energy. It's just, but the fact that our motors overheat. So at some point, the motors will get so hot that the glue that bonds the magnets in the motor to its backing will fail. There's something called a glass transition temperature, which if a material of that kind achieves a glass transition temperature, it dramatically loses its strength. So we don't want to push that limit. We pushed it once earlier in the mission in order to really do some tremendous science. We flew across that vast Zeta region, which no rover could drive, and we sort of got ahead of the rover by a whole number of weeks so we could do the recon. For that one flight, I was willing to push the limit beyond the normal design limit of 90 seconds to closer to three minutes, because it really made the case to the scientists that this is a valuable thing. But once we did that very risky, high payoff flight, I stepped back and I said, okay, that's nothing bad happened there, but we're not going to try to reach that limit anymore. So since then, we have been keeping that as our thermal limit, and that translates to 3 minutes of flight for this helicopter. Yeah.
Just a follow-up. So have you considered 3 minutes out and landing and waiting and then coming back?
We don't come back anymore. Before, we used to go and come back thinking that we would recon for our own flight. Let's go there and make sure there's a decent airfield there, come back and think about it. But now, since we're aiming for gentle sand dunes, and we've done it 26 times without any recon, it turns out that it's been pretty robust. The orbital images are pretty darn good for identifying decent helicopter landing fields.
Thank you.
Yeah, maybe if you want to ask a question, come to the center so I can hand the microphone easily.
Thank you. What would happen if you tried to fly Ingenuity here in this atmosphere?
Well, there's a version of it that if you come tomorrow, will fly here, which is, but the blades spin only at 400 RPM. And this is just It's basically an RC joystick control. There's no autonomy, there's nothing. It's just the mechanical hardware is leftover parts from Ingenuity that Matt Keenan and his team built for this terrestrial Ingenuity. They call it Terry, I think, terrestrial Ingenuity. So you can see Terry fly at 400 RPM, but if you try to spin those blades in this thick atmosphere at 2500 RPM, basically, you just basically stall out and burn out the smoke or tube. It's just like, I think Matt made the analogy, it's like trying to take an RC plane and trying to put it under the water, right? It just wouldn't be able to keep up with the torque demands of trying to fly under that such a drag-heavy atmosphere.
Thank you.
Anybody else? I can't quite. Yeah, if you come to the center, please, that we can
Sorry.
do the back and forth on the microphone easier.
Do you plan on what are they bringing it back here? Like what time? Like, is there like a plan on when they're gonna bring it back? Or if not, is there a plan to send a second one?
Yeah, so NASA's emphasis right now is to bring back these sample tubes, and we hope to bring back, I think, 30 tubes. Each tube is 150 grams. And that in itself is a major challenge to have a Mars rocket that takes off from Mars, rendezvous with a satellite in Mars orbit that then brings the samples all the way back to Earth. So there are no plans to bring back anything other than extremely scientifically valuable things back from Mars to Earth. So no, so this will be, hopefully someday the National Park Service of Mars will set up a Wright Brothers Jezero National Park Service, and somebody here who wanted, there's a park ranger somewhere who wants to go to Mars, there she is. So she'll be there and she'll give you the spiel, you'll be there in your little spacesuits and hear her talk about it. So, but yes, based upon the success of Ingenuity, and to be perfectly honest, the sort of unprecedented success, we are now sending 2 more helicopters in this backup role to provide an alternative ways of getting those tubes back to the rocket in case Perseverance itself cannot do the job. So yes, there are now an approved mission to send 2 additional helicopters to do that job. We've also been working on the designs for a Mars science helicopter, which are about 50 pounds. So think of 6 Ingenuities in a hexacopter kind of configuration. Would carry about 10 pounds of science instruments. And so you can actually do science and really exploit what I call as the 3 R's of helicopters on Mars: reach, range, and resolution. You can reach places that no rover can ever get to. You can't carry all the science instruments that a rover could, but you can definitely carry maybe up to 10 kilograms. Range, we can go many kilometers a day. Even this little guy can go, almost a kilometer. And the resolution, right? You saw what imagery up close does compared to orbit. So given those 3 R's, not reading, writing, arithmetic, the reach, range, and resolution, there's a very good possible future role for a Mars science helicopter, and we're doing some early design studies to see what that could be. But that's not been approved or anything, that's still in the works. But 2 Ingenuity class helicopters, basically Ingenuities with a little bit of an addition of some surface mobility by adding some small wheels, a small robot arm to pick up the sample tubes. Those have been approved and will be going to Mars in the next few years, yes. I don't want to keep people here more than the assigned time, so I just want to make sure that the Park Service is okay with questions. Are you guys good? You good?
Yep.
Okay, then please.
Question for you. You've talked a lot about helicopters, other vehicles, whether a blimp or dirigible, some kind of alternative that you've considered?
Yeah, back in the 90s, actually, I did a study to look at a Mars balloon system, and it's feasible. There are some disadvantages in terms of a balloon system on Mars or a dirigible system on Mars, and the real snag is getting it inflated safely. That has proven to be a thorn in the many attempts that have been made to do it, but not to say it's not possible. And in terms of station keeping, a helicopter can get up close and sort of station keep in front of something interesting, land in places. Things like regular aircraft just have to fly by. If you don't keep flying at a high speed on Mars, you don't stay in the air. You have to fly fast in order to generate enough lift. So just whizzing by something, while it might be perfectly good for maybe taking a grand tour of the Grand Canyon very quickly on Mars. You know, the beautiful Grand Canyon, Palis Marineris. For actually stopping and looking at things, you need an airfield to land and take off. So maybe something like a tail sitter, you know, which basically transitions from hover to flight, is a possible design. So a lot of these things are possible, but I think a helicopter has some distinct advantages in terms of being able to do up close and personal kind of science at Mars.
What about a fixed helipad? Something where you could have heating that wouldn't be required with...
But then you're constrained to where that fixed helipad is. One of the advantages of a helicopter, especially this helicopter, is sort of electronically tethered to the rover because it relies upon the rover to do the relay communications. The little radio on the helicopter can only talk to about a mile away, about. But future helicopters will have their own ability to talk to the orbiter relays that are on Mars already. And once you have that, you're not leashed to a rover or a landing pad or anything, and you can just head off, you know, into the distance because you will directly be able to talk to Earth from the helicopter. So that's the main advantage of having a free-ranging helicopter as opposed to one that has to come back to base. But I think if humans ever get to Mars, I'm sure they'll have a Mars base and they'll probably have a recharge and landing pad just for, you know, the helicopters. I'm sure that'll be there, but that's well beyond my lifetime, I think, the way things are going with the human exploration. So we'll see. Okay. Thank you very much, and thank you to the National Park Service for hosting this. It's been awesome. Thank you.